we'll move right on to the next talk, Renee Weber, who'll be talking about understanding the geophysical environment in the field. Thanks very much, Renee. Please take it away.
Me all right?
Yep, loud and clear.
Okay, great. Hi, everyone. I am here to talk about doing geophysics on the moon, one of my favorite topics. If I could go ahead and get the first slide, I'll go ahead and start. So just to sort of loop back to Sam's presentation from earlier, I wanted to highlight the science drivers for geophysical measurements on the moon. And I've got two sources. The first is from the agency's Artemis plan, which lists 7 science objectives that the Artemis 3 science definition team then went off and expanded upon to build that initial science campaign. So of those science objectives, 2 of them are primarily addressed by geophysical measurements. And 3 of them are, and those are the green ones, and then 3 of them are sort of, supported by geophysical measurements, and those are the blue ones. And both of those fall under the deployed instruments and the in situ experiments sections of the recommended campaign in that science definition team report. So those are the types of investigations that focus on understanding large-scale planetary processes like planetary formation, planetary differentiation and evolution, and on the moon, things like the formation of the magma ocean and the formation and evolution of the crust, the mantle, and the core. And then also, very important for understanding character, origin, evolution of lunar volatiles, is the temperature distribution within the planet. And so that is something also constrained by surface geophysics. So the other source that I've cited here is the Planetary Decadal Survey, which actually recommends a dedicated lunar geophysical network mission as it's among its highest priority robotic missions. But then there's an additional recommendation that conducting decadal level science should be a central requirement of the overall human exploration program. And so there are, some pretty strong justification for doing geophysics on the surface of the moon during Artemis. Next chart. So geophysics is the primary direct way that we have to probe the interior of a planet. Among deployed experiments, different types of investigations and measurements could capture seismic properties, heat flow I already mentioned, electromagnetic properties, and geodetic monitoring. And for in situ measurements, we can have anything done along a traverse, whether it be a walking traverse or a rover traverse. So those include things like gravimetry, magnetometry, or ground penetrating radar. And also very important is looking at the geotechnical properties of the regolith, since most of the types of investigations and measurements that you would want to take involve putting some type of instrument directly in contact with the ground. So looking at the density and porosity of the regolith, compressibility, shear strength, and permeability are all very important measurements. Next chart. So I wanted to talk very briefly about sort of different types of field investigations, and that would be trying to constrain global structure versus trying to constrain regional structure. And I will just use seismology as an example, since that's my particular area of expertise. So for to constrain the global structure of the Earth, in terrestrial seismology, we use a network of globally distributed seismic stations. And that's the map on the upper left that shows the global seismographic network. The stations are typically deployed in permanent vaults that are directly coupled to the ground, where you can either minimize or mitigate potential sources of noise. You put it far away from things that create noise. You can put it in a thermally isolated vault. You can pour a concrete footing. There's all kinds of different things that you can do on the Earth to create a very sound and quiet vault for your seismic instrument. So that's the picture on the lower left is an example of a permanently installed seismic station in a vault. So these stations are obviously long-lived. They record natural seismicity, so just the regular earthquakes that the Earth generates as it sees fit. And those are typically used to constrain global structure in one dimension. So to create a profile of seismic structure, which is seismic velocity and density from the crust to the core. On the other hand, we have regional structure. To constrain regional structure terrestrially, we typically use a survey style deployment where the stations are temporary, they're easily installed and easily removed. In the picture on the right, you can kind of see that's me down by my feet. There's a plate, a little metal plate that I'm about to whack with that sledgehammer to create artificially induced seismicity. And then right next to it and all along that line leading back to the truck is a line of geophones, which are just pushed into the ground with your foot. And those are typically used to constrain regional structure either in 2 or 3 dimensions, depending on the density of stations and the number of times you whack that hammer. So global structure kind of helps us to get at big picture science questions about the formation and evolution of planets, where regional structure tends to provide context for that global structure and also enhance field geology and sample collection activities. So right off the bat, when you talk about doing seismology on the moon, you're sort of looking at a hybrid of these 2 types of deployments where you may wish to take measurements that are going to constrain global structure, but you're very much in a field survey mode while astronauts are out on EVA. Next chart, please. So there are some factors that we should be mindful of when planning for geophysical investigations during the Artemis surface missions. So I've listed here several of the factors that influence geophysical data quality. The first is the landing site. Obviously, safety is the primary driver for both robotic and human missions. And so as a result, you may not get to land in the place that you find the most scientifically interesting or the most beneficial for the type of measurement that you want to make. You have to consider the proximity to potential sources of noise or signal contamination on the instrument that you want to deploy. I'll talk about that a little bit more in the next couple of slides. And then also you have to think about the distribution of the measurements. Do you want to have multiple diverse and dispersed sites, or do you want to have repeat visits to the same site? And then you have to try to pair those with the architecture of the mission that you're doing your investigations on. Another consideration is illumination, especially important if your instrument is intended to be, sort of left behind. If you need to have solar power, is it sufficient for the longevity of your instrument? You have to think about the diurnal thermal cycle, which can induce trends or noise in the data that you gather. You have to think about those geotechnical properties I mentioned. So for seismic measurements, we knew from Apollo that the regolith caused a lot of scattering and reverberations that are sort of a source of contamination of seismic signals. And some instruments can require burial in the regolith and can be sensitive to human-induced albedo and surface changes. Lastly, deployment and ground preparation, very important. Most geophysical instruments require moderately level ground with navigable rocks and debris. And then there are, of course, many instrument and measurement specific factors to consider. So the rest of my charts are essentially a series of case studies from Apollo geophysical instrumentation, some of the challenges that were encountered and how measurements sort of evolved over the course of the Apollo program to try to mitigate those challenges. Next chart. So first I'll talk about seismometers. There were seismometers deployed on every Apollo mission, starting with Apollo 11. The top right is a diagram of the sort of concept of operations for deployment. At the top level, it was take it out of the LEM, put it down on the ground, unpack it all, point the antenna, turn it on, make sure everything is working, and then move on to the next experiment. So there were several sort of deployment influences on the data resulting from that seismometer. First was just proximity to the LEM itself. The LEM became a source of noise. Seismic signals that were generated inside the LEM included venting of gases, circulating fluids, and actual just thermal deformation of the LEM itself. And then also the instrument sort of had lower efficiency for thermal insulation. And so it was not able to detect gravitational tilt on the lunar surface. Next chart. So Apollo 11 seismic instrument was a solar-powered instrument, and so unfortunately, by the time Apollo 12 mission landed, it was not operating anymore. But starting with Apollo 12, all of the ALSEP experiments were connected to radioisotope power thermal generators, which made them live for a very long time. And so starting with Apollo 12, we were very fortunate to have a permanently operating seismic network on the moon. And the picture on the upper right shows sort of a cross section of the moon with the near side on the left-hand side. And those little pink squares are the approximate locations on a great circle of the seismic stations. And then that image itself is sort of a cartoon of the type of science that we can get out of having a seismic network. So we want to be able to figure out, what's down there, what is the core, what is the structure of the core, where are the moonquakes, how deep are these discontinuities, things like that. So learning from Apollo 11, the subsequent Apollo seismometers were wrapped in these mylar skirts for thermal insulation. That was eventually found to actually introduce other types of noise. Also for Apollo 12 and Apollo 15, the crew tried to prepare the surface for placing the experiment by tamping the surface of the soil down with their boots. This didn't ultimately seem to be effective because they weren't able to get a significant amount of compaction. Next chart. So this chart also shows some other deployment influence on the data. There was a requirement in the concept of operations to orient the cable that came out of the seismometer toward the central station. And it's thought that because of the stiffness of that cable, that there was actually an amplitude bias introduced into the signal as a result of that. So those are just some examples for the seismic instrument of the way that deployment can affect the data that's returned. Next chart. I also put in a chart about active seismic experiments. I think, unfortunately, just in the interest of time, because I can tell I'm not going to have enough time to make it through all these, I'll skip this one. So chart number 10, heat flow experiment. So heat flow and measuring the temperature profile of the geothermal measurements help track heat production and the temperature distribution in the interior. In this slide, I have pictures of the Apollo 15 and 17 installations. Holes were drilled into the surface using the hollow drill stem. And once a hole was drilled, then the probe was placed down. A cap was put on it, and then a cable was fed from that back to the heat flow electronics package, and from that back to the central base station. So the picture in the middle is Apollo 15, shows the probe. Apollo 17 shows the heat flow electronics package. Next chart. So Tony, I'll just watch the video. Okay, so let me just talk really quickly. On Apollo 15, so there were 2 probes deployed on 15 and 17. On Apollo 15, only one of them was actually successfully placed to the full depth. There was possibly some kind of obstruction or other problem in the hole, the second hole, which is the one shown in the diagram on the left, possibly due to the separation of the stem that happened while the crew were trying to, overcome the difficulty of drilling down in there or sticking the instrument down in there. So there was a redesign for both Apollo 16 and 17, but unfortunately on Apollo 16, there was an accident in the field where the cable got ripped out from the base of the central station, and unfortunately there was no heat flow experiment data returned from Apollo 16. So the video just shows that, but we don't have time. I'm really sorry. It's just a couple minutes long. You can find it on YouTube. But basically what happened was Zhang accidentally tripped over the heat flow cable and just sheared it off at the base of the ribbon cable. Next chart. So another interesting way that deployment and how it's done can impact the data is the surface thermal properties. Surface thermal properties very important in recovering subsurface temperature. And it was found post-mission that the regolith on the footpaths of the astronauts turned darker. And you can actually see that in LROC images taken from orbit. And that lowered the albedo. And so as a result of the astronauts' activities, the solar heat intake by the regolith increased slightly on average, which resulted in a warming trend in the data that sort of took a long time to understand. And so another thing to think about is the thermal conductivity of the instruments themselves. As you're inserting them into the regolith, heat can conduct down the drill, and the heat that you introduce can take a long time to dissipate. Next chart.
Wrap up, Renee.
Yeah, I will go ahead and skip to, let's do chart 14. I just want to talk really quickly about mobility. Mobility was a recommendation out of the Science Definition Team report because of the incredible amount of diversity and, just distance and the amount of stuff that you can bring along. There were geophysics experiments that were taken along on LTV. The one that I've shown here is the transverse gravimeter. So I just wanted to put in a plug for mobility, and then I'll go on to the last chart. So obviously, there were a lot of instruments that I left out of this presentation and didn't even, in fact, have time to talk about the ones that I left in. There were a lot of different geophysical experiments done on Apollo, and that's potentially, a point of discussion for future workshops, or I'm always happy to talk offline if anybody wants to talk about LSEB. It's one of my favorite things to do. I just want to reiterate, geophysics is the only direct way to probe the interior of a planet. Key geophysical investigations are enabled by having humans on the moon, and there are many, many valuable lessons from Apollo for future instrument design and instrument concept of operations. Thank you. Sorry for going over time.